Right now this thing's playing in DME mode, so that's good because I can switch it back to transponder mode and show you what's going on with the transponder. We'll start out here in the middle. Transponder frequency, whenever you're going to use this with a transponder, you need to set this center thing up so it says 1030 and it says transponder. That sets it up for transponder stuff, the correct transponder frequency. The displays on the top are pretty much readouts of what's going on, what you're reading from the transponder. I have a transponder connected up right now, so we're getting our power output, we're reading the frequency, seems to be relatively accurate, and we're showing 100% reply, which means for every interrogation coming out of this test box, our transponder is making a reply. One of the tests that you do for transponder is an MTL, minimum trigger level, and that's the minimum number of negative dBm or microvolts that it takes to get 90% reply, which means that the transponder is going to reply 9 times out of 10. So if I reduce my signal level down here, I get down around 74, 75 in there, then we'll see our percent reply go down. At 78, it's down in the 70s, 60s. At 77, it zips right up to 100. So the question is, well, we know, for example, it's between 77 and 78, but if we'd like to know exactly what it is, we can use our S1403 adapter up here because it has a feature where you have fine-tune control over the output attenuator. And we can do that by taking our cursor and moving it over to where it says RF level. And when it says RF level, then we can slew it in tenths. And if I go in the negative direction, then I can get that thing pretty close to 90. And therefore I can say that at negative 77.7 is the exact minimum trigger level point on there. So I'll just go around and show the different areas. If we'd like to see the transponder code, we have a display selector here. I can rotate that over to transponder code. It's showing 3333, which if we look at the face of our transponder, we'll see that it indeed is set for 3333. Our ident will come up in here as well, and I'll let you know that our ident switch on this particular transponder doesn't work. However, our ident switch on the test box does. It is a toggle switch, but I want to treat it like a momentary. So you turn it on and off, and you'll see that ID comes up. And that's telling you that the identifying pulse is present. And if we look over here on this oscilloscope, I have this oscilloscope set on transponder, and we can see that SPI pulse coming up. And then it goes away after it times out. For Pulse Lab 1, for the ATC 1400 lab, you'll actually be looking at the generator pulses. And you have your choice of which scope to use. For demonstration purposes, I've got the Philips connected up for the generator output, and I've got the Hewlett-Packard hooked up for the transponder output. You can see there's P1 and P3 are being reported on the Philips. You might ask yourself, well, where's P2? Well, the P2 control is right down here where it says SLS echo. There's a toggle switch to turn it on, and then there's a thumb wheel switch to set the difference in dB between P1 and P2. Right now it's set to -9, so if I turn it on, it'll come up, P2 comes up on the scope, and but because it's so much less than P1, the transponder still continues to reply at 100%. What's going to happen if I set P2 to be 0 dB difference between P1 and P2? Percentage will go down. Right down to 0 probably. So I set it to 0 and sure enough it goes right down to nothing. Okay, so my P2 is now the same height as P1. That means the transponder is detecting a side lobe. It's not going to reply. Under most circumstances, unless we turn that on, the generator is only going to create P1 and P3. We'd have to turn the SLS on to get the P2. There's a transponder pulse width control that we will, for virtually all of our tests, I don't think there's any reason to take that out of Cal. I have that set, the thumb wheels on the top set the interrogator pulse width. If, for example, I set this at 0.4 and turn that control on, then I've reduced the width of my interrogation pulses down to 0.4 microseconds wide instead of the specification, which is 0.8. You'll notice my transponder noticed the difference and stopped replying. I went right down to 0. So just run that in Cal all the time. The DME P2 deviation we'll talk about momentarily, and I'll come over here and talk about P2 and P3 deviation. It's important that our transponder be able to distinguish between an A mode interrogation and a false interrogation, or a C mode or a false. And what is a correct A mode interrogation, time-wise? 8 microseconds. So if I have this plus delta and this minus delta here. If I set that to 1, my deviation to 1, and I press plus delta, that moves my pulse from 8 microseconds to 9 microseconds. That is not a valid interrogation. You'll notice it went down to 0, and if I flip back and forth, you'll see it move on the scope. You'll see that time moves. Same thing if I go from 8 to 7. You'll see the pulse move. You'll see that the transponder stops replying because 7 is not valid, 8 is. I can do the same thing with P2. I'm going to turn my P2 on. Okay, we're simulating a side lobe here, so the transponder stops replying. That also is dependent on P2 being in the correct spot. So I can deviate P2 as well. If I add a microsecond to that, now P2 is 3 microseconds away from P1. Well, that's not a valid side lobe suppression pulse. Therefore, the transponder replies. Likewise, if I move it down to 1 microsecond difference instead of 2, that is not a valid side lobe, and a transponder will reply.
Is it possible to widen the screen resolution on the Philips oscilloscope?
Yeah, it is. And
Hard to see.
the reason I have it set that way right now is this is a good time to talk about this one. If I go over to C mode, and what's my C mode? What's my C mode time? 21. That's why I moved. That's why I had it set the way it is. So C mode now with C. Let's see. I got 0% reply. Why would that be? Because I'm Cal here. Oh, let's turn that back off. C mode. We discovered a glitch on this thing this morning. My C4, somebody wired the C4 pin up to the wrong spot. So that's something we've got to look at. But down is on these switches, and the typical one way of testing C mode is to simply turn on the switches and see the pulses come up. Okay. Not all pulses will come up because they didn't put the necessary chips in for some of the deep pulses because the transponder will never fly that high.
So now what happened to C4?
I'm not sure, but we had some broken wires on there last semester, and I had somebody wire them back on, and I think they wired C4 to the wrong spot, because what we discovered this morning is when I turn on C4, it kills all the rest of them. So, I gotta check that harness, figure out what's going on. I don't want to leave C4 on too long, because I don't really know what's happening in there. All right, so,
That's cool.
so I'll look at that as soon as I get a chance. This is our pulse repetition frequency, how often the transponder is interrogated. If I turn that completely off, and actually I'll go back to A mode here. If I turn that off, then it just goes off and the transponder is not going to be replying. So I need to have this on throughout my test, and I need to set this at really no lower than 200, and I definitely don't want to put it up around 1,000 or so.
And what's that doing?
This is how many times per second this box is asking the transponder for information.
That's cool.
Okay.
So we can set that up to like 4,500?
Well, on the S mode, I don't think you're going to hurt it, but if you're on standard aircrafts, if you go up above 1,000, you risk burning it up.
That's what I want to know, because that's probably what I would have stuck up to.
Down here at the bottom, we have a frequency manual step, auto, and manual. Auto works for transponder, but if you're in auto mode, you don't have any control up here. It just stays at 1030. If we go to manual, then we can change our ground station or ATC 1400 frequency, and if I change it far enough, we'll lose it. Okay. So this actually would be 1036.
How well does this explain this in the manual?
Pretty well. And then delta minus, now we're going in a minus direction. It works a little better in a minus direction. We have to get down to 1022 before it cuts out.
Cool.
S mode stuff. We haven't, in either lecture, we haven't gotten as far as S mode stuff. S mode stuff is controlled with the S mode 1403 adapter. And we have different function numbers. The first function number 1, is standard ATCRAB's operation. Okay. If we go second function number 2, now we're in sequence mode. And if you look on the scope, you'll see that interrogation coming from the test box changed completely. Mode S is a whole different animal. Right? You've got 2 pulses and a data block. Now with sequence mode, it's running right now. Well, I should have recycled this, but there are different sequences. So if we go to second sequence number, you'll see that I've got sequence number 4 turned on. That's umplik format 11, and the address I'm using is all 7s. That causes the transponder to report its unique individual address. Every Mode S transponder has a unique individual address, so they can be called individually from the ground. Now the tricky thing about this is there's sequence number 1, and if I rotate this fast, I can get all the way up to sequence number 16. There are 16 different sequences that this could use. Now the tricky part is that when you first turn this on, 8 of those are going to be coming on at once. In order to get proper operation, you have to turn 7 of them off. And the way we turn them off is with this on cal button. So I just turned sequence 1 number on. number 1 on, notice how my percent of reply dropped to 50%. That's because it is interrogating sequence number 1 and sequence number 4. Sequence number 1 doesn't have an address.
Oh, so that's why it says my reply because it's an address?
Yeah, and let's just, for fun, let's put in an address. I think it's 603612334. Enter. Now it's not going to like it. I either put the wrong address in or something. So we normally, the first step in doing the S-mode stuff is to turn all of the sequences off except for one of them. And I really wish they designed that a little bit different so that only one would come up and you could turn other ones on as you needed. But they didn't do it that way. So there's 8 of them, and sequence, if you turn 1, 2, 3, 5, 6, 7, and 8 off, sequence number 4 is already preset for the test that they call for in the manual. Okay, other functions, second function number 3 is something called an all-call short. And you'll notice when you look at the scope over here that we get another pulse. There is now a P4.
Where's another pulse?
Right here. 1, 2, 3. If I turn the SLS on, then you'll see P1, P2, P3, and P4.
I thought we had 3 originally anyways.
You had 3 originally.
So how did we
You get into this S-mode stuff, they throw a 4th pulse at you. Okay. So, and function number 3 is an all-call short. A lot of these we're going to talk about when we get to S-mode stuff. Second function number 4 is an all-call long, or it makes that P4 wide. Second function number 5 is an interlace ratio, where this box is showing 0% reply because the 1400A can't really keep up with what's going on. But if we look up here on the 1403 adapter, we see that we're getting 100% ATC and 100% out mode S. So what the box is doing in this case is it's alternating back and forth. A mode, S mode, A mode, S mode, A mode, S mode. Okay? This box can't handle that complexity. The one on the top does. So you can see your replies up here. There's also a function number 6 that we don't actually use, and we are getting 100% on there, but that's really a function number for a different type of test. So we will be using function numbers 1. Give me second function 9. We're using the ACRABS function, which is 1. We'll be using the sequence mode, which is 2. All-call shorts and all-call longs is pretty much what we use with this. The interference pulse, now we're back to a normal standard ACRABS interrogation. We could put a interference pulse in if we want. It's going to put in a 4th pulse if we can get it in place here. I think we got to turn off the S mode to get it. Well, it's hard to see on the scope, but you see how that moves? See how the display on the scope moves? Because we're putting an interference pulse in there. The interference pulse will trick some of the decoders and allow us to use secondary decoders on there. Most of the time we'll run that off. Okay, we're going to put the oscilloscope through its paces. Currently we have a KT76A connected up to the ATC 1400A. and we are looking at an A mode reply 7777. And as I change the pulses, you will see the display change. There's 0777, 0707, 0007, and all zeros. There's A1, A2, A1 and A2, A4, A4 and A1, A4 and A2, and all three A pulses. And we'll repeat for B. There's 1, 2, 2 and 1, 4, 4 and 1, 4 and 2, 4, 2 and 1. C pulses 1, 2, 2 and 1, 4, 4 and 1, 4 and 2, and all three. And finally D. D1, 2, 2 and 1, 4, 4 and 1, 4 and 2, and all three pulses. And finally the SPI, or ident pulse, that comes up at 24.65 microseconds from P1. That leads us to the next test, which is to test the time from F1 to F2. We can do this by going to delta T, delta V. We can move a start marker up to the beginning of the first pulse. We can move to the stop marker and move that to the beginning of the last pulse. And then right here we read as 20.3 microseconds. Now if we would like to spread that out, we can move to our time base, and we will use our microseconds per division, or our time per division, and we'll begin spreading this out. And we should be able to spread it out as far as this. Go back to the delta T, take the start marker. The best place to measure this is at the 50% point. It is the only true way to test it. And move the stop marker into the 50% point, and we see that we are coming up with a delta T of about 376 nanoseconds. So these pulses are a little bit narrower than they should be. They should be 450 nanoseconds, which would put them much wider than is currently shown on the screen. For rise and fall time, we'll go back to the time base, and we can spread it out even farther. And if necessary, we can change the delay until the rise and fall actually shows up. Now perhaps it might be a little bit easier if we did this on a 10 microsecond. Go back to our delta T, do a start time. We're doing the fall here. It looks like about 10% or 90. Move this down to about the 10% point. Seeing in the neighborhood of about 48 nanoseconds. That's fall time. Now if we go back to time base and change our delay, let's look at the other end of that pulse. We get better definition over here. Perhaps we can go to the 5 microsecond time period and get a better look at it that way. Let's bring in our start marker. Bring in our stop marker. And it looks like about 24 and a half nanoseconds. Ended up at 24.7. Back to our time base, and if we select nanoseconds per division, we eventually get to microseconds per division, and eventually we will see the whole display on the screen again. That was mode A. All of these would be repeated for mode C. In mode C, we can flip the switches on the LX3B and as I'm flipping these, we have all the A pulses and one B pulse. Then you'll see that now on the screen that we have those showing up, and I'll continue. B2, B4, C1, C2, C4, and D4. In this particular transponder, D1 and D2, even though I can flip the switch, those pulses are not present. Those pulses are not necessary because this transponder will not fly at a high enough altitude to require those pulses. Other controls on the scope would be a channel control. This is where we get our volts per division to make the pulses taller or shorter. We can offset, so we can move them up or down on the screen. We have our trigger control, where a dashed line will move up and down, representing where the trace beginning is, where it starts to draw the trace. That dashed line must be on the waveform in order to get a trigger. If you start this out and you see no triggering, then move the trigger downward until you get a display. In the display, you can control the number of screens you get. There's 2 screens, there's 4 screens, and so on. Normally we use it as 1. We can turn off the lines, make them look differently. Grid is typical. If we do not get a nice definition of pulses, perhaps our dots are not connected. So if you get a display that looks like this, go to the display and connect our dots. Delta T, delta V we've already shown. So we have our time base, our channel, trigger, display, delta T, delta V. And these buttons are multi-function buttons. Their meaning depends on what it says on the screen.